Hello everyone and welcome to another lecture. Today we want to talk about inner product. So far up until now we have only talked about vector spaces, their subspaces, fields and bases and dimensions of these vector spaces. But now we want to actually compute the products of vectors so that it will produce a number. Just like dot product in vector analysis. That is the ordinary or introductory vector, just like introductory vector analysis. And for that, when we deal with vector spaces, we call this product as inner product. So as I said, the idea is to recreate a version of dot product, and for that is creating a number out of these vectors. We need some more ingredients, and the key concept here will be the concept of dual spaces or so-called dual vector spaces. So first let's talk about dual vector spaces and then we'll move forward to inner products. So the idea of dual vector spaces is the following. So let me just write dual vector space. This dual vector space is given by the following definition. So let's write definition. So we call this definition as the following. Given a vector space, let's say V, given a vector space V which is defined over a field F, or we could write K, but this time I'm just introducing field with F. The corresponding dual space by corresponding I mean the dual space to V is denoted with V star, and it is a set of all linear maps let's call this map phi, such that this map takes the elements of V and map them into the field. So what does this long definition really means? Let's try to break it down. So if I want to draw a diagram, let's draw the diagram for the field. So let's say this is my field. Here each and every point will represent some numbers that can be in general complex, and let's denote our vector space V as this. So here all these points, let's say, will represent some vectors, and there is a map between them. This map takes a vector from here, and this map is called phi, and it will produce a number out of these vectors, and the way we write it is phi V, and this maps to F, that is, it will map to the field. So this is how this abstract definition works, and this is the picture, but this picture is also not that clear, right? That is how this map will work. That's the question we want to ask. So let's try to visualize this in a manner. Recall the product of a column matrix with the row matrix gave us a number slash scalar, right? So the idea is the following. For vector spaces, you have, let's say, some vector v, and to produce a number out of it, we introduce something called a v-bra, which is coming from the adjoint operation that we talked about in one of our earlier lectures, but there we didn't define it officially. And in general, the product, that is the product written like this. Let's say you want to multiply these two vectors. This will belong to the real number field. And here the terminology is this: if this element belongs to the vector space, this element will belong to the dual space. Now let's think of these V's as column matrices. Let's say 1 0. So this will be a row matrix, right? Sorry. And this will be obtained via the adjoint operation or the dagger operation. So if you recall, the dagger operation was transposition and complex conjugation together. So this will be just 1 0, and if I just evaluate this product, this is just 1 0 1 0, and this is just 1. And here, instead of the same vectors, I could take another vector, let's say w, and let's say w is denoted as 1 plus I, and again we have our v as 1 comma 0. So now I want to produce a number out of this. So again I can write it like this, which actually represents, this is called the sandwiching thing that we talked about in one of our earlier lectures, the sandwiching. Of brackets. And in fact, this notation together, where you have a bra and a get, it's called the bracket thing. So let's try to evaluate it. So the bra for w is 1 minus I, this is 1 0, and this is just 1, and again it's a real number, but let's try to see if we can get a complex number. So instead of v, let's write it as v prime. Instead of 0, let's write it as 2. So if we do that, then instead of 0 over here, we will have 1 plus 2 minus 2i. So this is 3 minus 2i. And this product v, this is called the inner product. So this is how inner product is defined. That is, you have a vector space, and from there you can pick up a vector, then you define a dual space of it, and then if you can define an inner product like this, that will produce a number, and in general that will be complex. And a space, a vector space where the inner product is defined is known as the inner product space, right? So this is how we can define an inner product, but to define an inner product we have to define this dual space thing first, and then after the inner product is defined, if we can take a vector space and define inner product for it, then we have a inner product space. So let's try to see some property of this inner product thing. So properties. The first property is that V inner product with W is the complex conjugation of, or that is the adjoint of this thing. And this is similar to the symmetry when we see dot products. That is, if I have two vectors, that is these vectors from our vector analysis courses, ax, ay, az, bx, by, bz, so a dot b is equals to b dot a. These two are similar. You can see this is also called the skew symmetric property. The skew symmetric property. And from this inner product, as we discussed earlier, the notion of a norm or notion of a length should emerge, and the way it emerges is the following. That is, if you take a vector and if you compute the inner product of that vector with itself, it should be always greater or equal than 0. That is, it gives us a notion of the distance. Why? Because if you think of the dot product between A and A, that gave us modulus of A, cosine 0, right? So it gave us the modulus squared, so that is the distance slash length squared. And here we have the same thing, almost same thing, but in fact now it is more generalized. So that's why in one of the earlier lectures I said that even for matrices there is a possibility that you can define a notion of a distance, and that is the trace norm. So instead of V, if V were not row or column vectors, if it were matrices, this would turn out to be a trace. So the reason we are saying that it is greater than and equal to 0, greater than 0 is understandable because this is giving us a notion of distance. So let's just write it down. This gives us a notion of distance. And the way it can be 0, if V is 0, only then this thing is 0. So that's why we are calling it the positive semi-definite property of the inner product. Positive semi-definite. And the third property that we want to look at is that the linearity in Ket. So we are taking this following product. So here we have some Ket. You could define it as, let's say, psi, and that psi is a linear combination of two Kets, that is W and Z, and A and C are scalars that corresponds to the field over which the vector space is defined. So the linearity in Ket suggests that this will be just a inner product of v with w, and it will be c v z. So this is what is known as the linearity in Ket. That is, if you have a linear combination, you can just combine them like before. And what if instead we had this thing? So again, we are denoting this with psi, and if you have noticed the first property that we talk about, that is the skew symmetric property, the answer is already evident to you, but let's just do it explicitly to see what happens. Again, we're gonna use this linearity. Again, note that there will be some star over here because these numbers a and c are in general complex. So when you take that dual component, I mean the dual vector of this psi ket or ket psi, this psi is defined as this operation, right? So when you do this dagger operation, there will be the stars over here. So if I do that, we have w v c star z v. This is nothing but a v w and c v z. This whole thing daggered. So this is sometimes also called as antilinearity of the inner product with respect to the first vector in the inner product. So this is just a feature, and you can easily see it from the linearity in Ket. And now, since we have talked about this notion of a norm, we finally define it formally. That is, norm, it is defined as the square root over the inner product of a vector with itself. This is how it is defined. It's called norm, or the length of a vector, or length of a vector. And with the help of the inner product, we can also define whether two vectors are orthogonal or perpendicular to each other. Recall, if I had two vectors a, b, and if a dot b was 0, we could say a and b were perpendicular, right? So similarly, in this case, if this inner product, let's say v and w, if this is 0, this v and w, they are mutually orthogonal. That means orthogonal to each other. And after this, we can go for another definition, that is a set of basis vectors of all unit norm. That is, since we are dealing with orthogonal vectors, we know that if I have some vector whose norm is 1, that is, we define norm over here. If the norm is 1, and let's say I have a collection of some vectors and each and every one of them has a norm 1, and each and every one of them are mutually perpendicular to each other, so we can say that these vectors are orthonormal to each other and they form an orthonormal basis. So orthonormal basis. This means norm of the vectors or the basis vectors vectors are 1, and the second thing is they are mutually perpendicular. And notice that this whole thing is similar to the vectors we see in Cartesian 3D or 2D coordinates and so on. And using this idea of orthonormal basis, we can write down the expansion of a vector in terms of them. That is, we can write down any vector as a linear combination of these orthonormal vectors. How we can do that? So how to do it, we will see below. So let me just scroll down a bit. Okay, it's scrolling down. So we can write a vector v as this, right? These components and these i's. But now I am calling this i's over here as orthonormal basis or orthonormal basis vector, whichever way you like it, and the other vector as let's say w, and let's just change the index for the summation. Notice that I am not writing from I1 to n, but I am meaning explicitly that this is a finite dimensional case. As I talked before, that we'll be dealing with finite dimensional vector spaces for now. So if you want, you can just write it like this, or you can just leave it blank. So for today's lecture, I'm gonna leave it blank. So now what happens is that you write wj and you write the another orthonormal basis vector, right? So what we can do now is that we can try to take the inner product. Notice that this v and w, they belong to the same vector space. The reason I'm using I and j, just to let you know that these are just dummy indices and they get summed over. So the only thing that is different is the components, but the basis vectors are the same. So just I'll put an arrow to it. And now we want to compute what is v inner product with w. So first of all, let's compute v. This comes from the complex conjugate, the dagger operation or the adjoint operation of this. So let's write it explicitly. I, vi, I, and you have a dagger operation over here. So this will just give you I, vi star, and you have this bra y, right? And then what will happen is that we are computing this. So let's just write this down. So there is double summation, one is over I, another one is over j. So you can write v star, wj, then I and j. This sandwiching is as before, like we did for this vw. And notice that whenever I and j are not equal, this inner product is 0. 0 when I not equals to j. And this is 1 when I equals to j, because these are orthonormal vectors, and that's why their norm is 1, and they are also orthogonal or perpendicular to each other. So when you dot this, I mean when you take the inner product of it, if they are the same thing, let's say instead of I and j you had 1 1, so that would give you 1. But if you had 1 2, that is instead of I you had 1 and instead of j you had 2, that would give you 0. So this is coming from this orthonormality condition, and we want to denote it in a new manner. So now I want to write this I and j's over under a single summation notation. Then I write vi star wj, and this is the new thing that we are introducing. This is called a Kronecker delta. And this Kronecker delta has this property that whenever these two indexes are same, this is 1, and whenever these two indices are different, they are 0. And now both of these indices are summed over, and if you get confused that what is the limit for the sum, you can always go back and type n above this summation, since we are considering an n-dimensional vector space. So notice that the only non-zero contribution, or so to say the non-trivial contribution, will come from whenever I is equals to j, right? So whenever I is equals to j, this is just 1. So what happens is that this Kronecker delta will now eat up one of the indices from here. You can either kill I or kill j, that's up to you. So because of this, we now write j, that is I is equals to j, so that we get a non-zero contribution. So let's write vj star wj star, and this is just delta jj, right? And all the j's has been summed over. So this step is actually not necessary. From here you can contract these j indices and replace these j's with I or i's with j, whichever way you want. It doesn't matter because it's a dummy index. It gets summed over anyways. So the final result is that j vj star wj, because this is just 1. So this is how you can compute the inner product of two vectors. And after this, there is another thing that I want to show you for today. Notice this expression over here. Let me mark it with a red mark. This is similar to our matrix multiplication. Why am I telling that? Because if I write I and j, oops, I, j, v star I, if you just put this delta in the middle, this is actually similar to a matrix multiplication. And if you think of it, this v star is actually like a row thing. This is a matrix, and this is your column thing. In fact, when you have n dimensions, that is an n-dimensional vector space, this delta ij will correspond to, if you take the matrix representation, it will correspond to a n cross n identity matrix. This big to zeros means all the entries are here is 0. So this is a n cross n identity matrix. And this will be it for today. Thank you.